We have two main types of reactors, flow and non-flow reactors. The first one will be the batch reactor, basically a bucket and a stirrer. We have the CSTR, or also called the MFR, continuously stirred tank reactor or mixed flow reactor. Let's call it MFR to emphasize the mixing process. It's basically again a bucket and a stirrer, but this time we have flow into the system and flow out of it. The third one is the plug flow reactor, PFR, which is basically a long tube and flow into the system at the beginning and flow out of it at the end. In the two tank reactors, we assume perfect mixing and a uniform concentration profile in the whole tank. In the PFR, however, we only assume perfect mixing in one differential element. So in like one tiny piece, looking at it from the side, it's like with length dx, and a different concentration profile along the reactor. So let's take a closer look at the concentration and how it changes down the reactor. First, for the batch reactor, all of the reactants enter at T equals 0 with the concentration of C0, and the longer they stay in the reactor, the more will get converted. As we assume perfect mixing throughout the tank, there's no change in concentration along the radius or the length. For the MFR, we assume a uniform concentration profile again, but we have an inlet and an outlet, and we achieve steady state at some point. So the concentration will basically be the same with any tank dimension, time, length, and radius. However, we can basically assume that at the inlet, concentration drops to the operating concentration, so from C0 to C, which is the concentration throughout the tank. And this also applies to any other tank dimension. For the plug flow, we assume perfect mixing in one differential element of length dx, so it has perfect radial mixing but no axial mixing. So with time, it achieved steady state. With radius, it is also constant, perfect radial mixing, but down the reactor, we have a change in concentration. So looking at them again, the batch reactor stays the same but changes with time. The MFR reached steady state, and the PFR has a concentration change with length down the reactor. So to better understand how the MFR or CSTR and the PFR are related, let's look at their concentration profile and how it changes down the reactor. Again, the CSTR or MFR has a uniform concentration profile in the complete reactor, and the PFR has perfect radial mixing, so one of these differential elements of length dx has a uniform concentration profile. Again, as before, concentration drops down and reaches the operation concentration until it reaches the outlet. For the PFR, the concentration enters at C0 and gradually decreases with x. Now let's assume we have one big MFR and split it into three equally sized smaller ones, but overall they have the same volume. The reactants enter at C0, they drop down to the operating concentration and reach the outlet. For the three CSTRs in series, the reactants enter at C0, drop down to the operating concentration of the first one. So we reach C1 here. Then they enter the second reactor. The concentration drops to the operating concentration of the second one. So C2 here. And then the concentration drops again to the operating concentration of the third reactor. If you compare this slope to one of the PFR, you see that the slope looks more and more similar as the one of the PFR. That is because if you take an MFR and basically flatten it so the height becomes dx, you basically get a disk. And this disk is one element of a PFR. So the more CSTRs you put in a series, it more and more starts to become a PFR, and you will achieve a stepwise concentration profile which looks very much like a PFR. So infinity, if you string together as many CSTRs as possible, you will get a PFR.